Ladies and gentlemen, good evening. My name's David Jamison. I'm the organiser of the School of Physics July Lectures in Physics program, and it's my great pleasure to welcome you all here tonight for our final lecture in the 2017 campaign. I've just returned from a tour of Europe, and on Thursday of last week I visited a laboratory where my colleague is building some very sensitive apparatus for trapping atoms of antimatter. And it's a great pleasure as a physicist to stand inspecting the apparatus while my colleague said, oh, this is the pipe where the antiprotons come in, this is the pipe where the anti-electrons come in, and here is where they combine to make anti-hydrogen. An atom of antimatter. And the whole idea of the experiment is to check which direction does the anti-hydrogen fall, up or down. So us physicists are waiting for the outcome of this experiment with great excitement. Einstein says it falls down, and I'm voting on down. All right, but let me introduce tonight's speaker. My friend and colleague, Martin Sevior, is the best person to talk to you tonight about antimatter in space. Martin has had a long career at the frontiers of physics. His research program, involving some of the biggest particle accelerators in the world, has been focused very much on the mystery as to why we are all made of matter and not antimatter, even though much of the physics suggests matter and antimatter should be produced symmetrically in the events of the Big Bang. So Martin is exploring the physics of what happened very early in our universe when all the matter and presumably the antimatter was made. Why is there no antimatter around today? Martin completed his PhD here in the School of Physics in 1985 and then spent a number of years as a postdoctoral fellow, including at the Tri-University's Meson factory in Vancouver in British Columbia. And indeed, during that time our paths crossed in my apartment in Pasadena, as we were both postdoctoral fellows in North America at the time. But enough of the introduction. I'd now like to invite Martin to come and tell us all about it. Martin.
Well, thank you very much, David, and thank you very much, everybody, for coming by today. Right, lights. Yep. So it's my great pleasure to talk about this subject. As David says, it's been the focus of my passion for my research for many, many years. I think it's a marvellously interesting question, and not only will we look at why there's more matter than antimatter around and what the mystery about all of that is, we'll also look at a very sophisticated experiment to actually look to see how much antimatter there is in space. So that's what this AMS experiment will investigate. Okay, so before I go any further, I'd just like to put out a couple of thank yous because we have some really fun demonstrations today. So first off, I'd like to thank Steve Damon, who put together our demonstrations showing principles of electrons, and my good friend and colleague, Dr. Graham O'Keefe from the Austin Hospital, who's provided me with some PowerPoints explaining positron emission tomography, and we have some really nice demonstrations about antimatter through some positrons. So we'll be playing with antimatter right here today. Okay, so brief introduction. So we know about atoms, so this is what we're all made of course, and when we touch one another, what we do is we press our electron probability densities against one another. So we only ever feel one another's electrons. Inside the atoms are the atomic nucleus. We don't get anything like strong enough to touch atomic nuclei together. And within atomic nuclei there are protons and neutrons. And then within protons and neutrons there are quarks. So ordinary everyday matter is made of up quarks and down quarks. But when you go to sufficiently high energies, you can make more exotic quarks, like strange quarks, charm quarks, bottom quarks, and top quarks. And they all have nice exotic names too. So, in pairs with these up quarks, down quarks, charm and strange, top and bottoms, we have things called leptons. So these are our familiar electrons, and then there's a partner of an electron called an electron neutrino. So electron neutrinos are very, very prevalent in our world and in our universe, but we hardly ever see them because they go through matter like, I don't know. I don't have a good enough analogy. I think the analogy is that if you had a light year of lead, the positrons coming out of our radioactive sources here, we have a few radioactive sources here, would just happily go through that light year of lead without interacting once. So they interact very, very rarely. Okay, so we have electrons, muons, which are just a heavier version of an electron, and tauons, which are a heavier still version of these. And then put these together with the bosons that bind everything together, like our photons are responsible for the electromagnetic interaction. So they allow our electrons to be attracted to our protons. Gluons, which bind the quarks together inside protons. Then the W and Z, which are responsible for the weak interaction, which is what makes our radioactive sources radioactive. And then the famous Higgs boson, which was just discovered a few years ago at CERN. Okay, now every particle in the Standard Model is accompanied by an antiparticle. They have exactly the same mass and size, but exactly opposite electric properties. So here are some matter particles, like our familiar electron, and there's an antimatter particle associated with that, which we call a positron. A proton, an antiproton, a neutron, and an antineutron. These all have exactly the same dimensions, exactly the same masses, but exactly opposite charges. Okay, so let's do an experimental test to show the existence of antimatter. So what we can do is we'll turn on our little demo here. We'll put it on the right VGA. Right HDMI. Okay, so here's an old-fashioned electron tube. Up here, right here. Okay, so there's a beam of light that you see exists. Oh, wonderful. Reset. Okay, beam of electrons, which we can make by just heating up a metal in vacuum. It boils off the electrons. We accelerate them up to, say, 700 volts or so, and then they just go flying up the screen. When they hit this screen here, they go flying up this tube. When they hit the screen, they make it glow. All right, so what we can do then is we can apply a magnetic field. When you have a charged particle in a magnetic field, what it does is it deflects the charged particle at right angles to both its direction of motion and also the magnetic field. So here is a magnet. It's the north side of the magnet. The magnetic field comes out of the north side of the magnet. These are electrons, so they're negatively charged. So it's like they're positive charges flowing downwards. Magnetic field in. My hand points in the direction of the deflection. So we take up our magnet, and we see that we can deflect our electron beam. Awesome. So all we have to do to show the existence of positrons is get a positron beam, throw it up here, and see it bend the other way. Unfortunately, it's really hard to get a low-energy positron beam. You have to do something like David's colleagues at CERN, to get a very low-energy positron beam. So rather than that, what we'll do, instead of having this wimpy little magnet, is have a nice big strong magnet, this thing here. All right, so we'll just turn this on. And what I've got here is a beta detector. So what this does is it detects high-energy electrons. You hear that sound? Every time there's a click, a high-energy electron has gone and hit the detector. Okay, so we'll take it out of there. We'll hold it up above here. We'll expose it and we get a nice signal from our high energy electron beams. All right. So what we'll do now is we'll put this electron beam through a magnetic field like this. We don't see much now because the electrons are all being deflected. Right? Right is down to the right. So we can detect our electrons over this side. But not on this side, because they're all getting bent that way. All right. So my colleague, Graham O'Keefe, has provided us with a nice source of positrons. Here it is here. So now, we don't get much over this side. We put it over this side. We now get a really nice big signal. Okay, our positrons are being deflected in the opposite direction to our electrons. So, we've got a great source of antimatter right in this little tube. Positrons coming out from this radioactive source. Okay, Steve, can you come down the front, please? And can you set that thing up on the detector? All right. So this is what we've done here. This morning. We had our electron source, strontium-90, which emits these negative electrons. They got bent one way. We have this gadolinium-68, which emitted positrons, and they got deflected in the opposite direction. Okay, so there's our high energy electrons and high energy positrons, which we just saw. So magnetic fields deflect moving charged particles. The direction is opposite for the sign of the electric charge. So when we had negative electrons, they were deflected in one direction. Anti-electrons, positrons, they were deflected in the opposite direction. Okay, so there's another really famous effect of antimatter. And that is, if you take a particle and you make it strike its antiparticle, they annihilate one another and they convert all of their mass into energy. So if you take a positron and you collide it with an electron, you get two gamma rays coming out. All of that rest mass energy from the electron and the positron gets converted into gamma rays. Similarly, if we take a proton and an antiproton and we collide them together, all of their rest mass energy gets converted into energy. So this together is about 2,000 times the amount of energy from an electron and positron. So I don't know if David talked about this on how to make things go very fast, but as far as we know, if you want to make a rocket to go an interstellar distance, you basically need a large supply of antimatter in order to get enough energy to do it. Okay, so this is our second experimental test. What we're going to do is observe matter-antimatter annihilation. So to do that, what we're going to do is stop positrons in matter. And we're going to observe how a positron and an electron, when they combine together, make two gamma rays. So here's our little radioactive source, our source of positrons. So we've got a proton which converts to a neutron, and it does that when its up quark emits a, I've got this around the wrong way. Its up quark emits a positron and converts to a neutron. So there's the positron going out. We get an annihilation, and then we get two gamma rays, one of which will go into our detector. Another one comes out, two gamma rays, and it goes into our detector. All right, so let's do a demonstration of this. Laptop HDMI, there we go. All right. Lovely. Reset. Okay, so here we have a very sensitive radiation detector. It's called a gamma ray detector. Okay? So what we're going to do is fire positrons from here up past the radiation detector, and there'll just be a few gamma rays that you see because we can't prevent all of the positrons from annihilating somewhere. Okay, so you start to see a bit of an accumulation there. All right. Now, if instead of just letting these positrons pass harmlessly up above our radiation detector, we instead stop them, what I suggest you do is watch how this peak changes. As this goes up, it's a sign that we have a positron annihilation. We have one of these gamma rays being emitted when the positron stops in our piece of aluminium. So I put our piece of aluminium in front of the detector, and yet now you can see the number of positrons annihilating really increases dramatically. So we're stopping positrons in front of our detector here, and consequently we're getting a lot of annihilations. So there you are, there's real experimental evidence of matter-antimatter annihilation. Okay, so positron emission tomography. Just make a little diversion into this because this is really kind of cool. This is applied particle physics. Okay, so what you can do is you can make a radioactive nucleus that is a positron emitter. Then you can attach that to an active biological chemical like glucose. Then you can stick this inside someone's body and you can watch where the positrons annihilate. Because what happens is we get this radioactive decay. Out comes the positrons. They rattle around inside the person's body, bouncing off electrons until they lose enough energy to get attracted to an electron, and they form a bound state of positronium. Then this decays and annihilates, and out comes two back-to-back gammas. So the cool thing is you can trace these gammas back to where they came from. You can draw straight lines between where they're detected and work out where in the body these gamma rays came from, and consequently you know where this radioactive glucose is actually being consumed. So this is a really useful thing. One thing you can do with this is work out how the brain works. All right, so if you put this radioactive glucose into someone's brain and ask them to listen to me talking, you see part of their brain light up. Here it is here. If you ask them to look, you see another part light up. There it is there. If you ask them to think, you see another part lighting up. There it is there. And if you ask them to move around, you see other parts light up as well. There it is there. So we can actually use positron emission tomography and this applied particle physics to work out how the brain works. So that's kind of cool, a nice application of antimatter. All right, on to a different topic, the history of the universe. So, we all believe, well, a large fraction of us believe, that the universe began with a Big Bang. And if we go back far enough in time, we go to a region of time and energy density where we don't know what the laws of physics were. Now, we speculate that there was this period called inflation early on where the size of the universe expanded exponentially. After that, it just sort of expanded essentially at the speed of light and just cooled down adiabatically. All right. So in this initial soup, there was an immense collection of energy. So we assume that the universe started from this state of pure energy. Then, because of Einstein's equivalence principle between mass and energy, what happens is this energy converts itself into matter and antimatter. So we can get a particle and an antiparticle annihilating, making two gamma rays. These two gamma rays can mix together and then make a particle, antiparticle again. So we have this soup of matter and antimatter and energy in the early universe. Now, as the universe expands, it cools. So as it cools, the amount of energy present reduces. You can only make as much matter as you have energy. And so if the amount of energy in the universe decreases, eventually you end up with matter. However, this matter and antimatter, if it's present in the same abundance, will then annihilate. The amount of energy that you get from that will be less and will decrease. And eventually there won't be enough energy present to make particles at all. So, in essence, because we start with the same amount of particles and antiparticles, what should have happened in the universe is that all of these particles and antiparticles should have annihilated, just like our little demonstration. Okay? We've observed that. Particles and antiparticles annihilate. If we have this massive amount of energy, we have to make the same amount of particles as antiparticles. Nevertheless, when they all annihilate, there should be nothing left. So all the matter and antimatter should have annihilated, leaving only energy. So the question arises, what are we doing here? So this is the case unless there's some slight favouring of matter over antimatter. So our observations today of the amount of baryons compared to the amount of cosmic microwave background is such that the imbalance between matter and antimatter is 1 in 10 billion. So this matter and antimatter almost exactly balances, except for this little part, 1 in 10 billion. So this tiny imbalance created all of the stars, galaxies, planets, and us. Okay, so on to my passion. What I'm interested in is these matter-antimatter asymmetries. And we can study them at the Bell experiment. Particle physics has observed matter-antimatter asymmetries, and one of the places we've done this is at the Bell experiment, where I've spent a great deal of time in Tsukuba in Japan. So my partner Trudy has waved goodbye to me many times as I head off to Tsukuba. Okay, at the Tsukuba laboratory we have the Bell detector, and in the Bell detector it's located at a point where we collide electrons and positrons at exactly the right energy to make short-lived subatomic particles called B mesons. So these collisions make B mesons in matter-antimatter pairs. Okay, we have an electron and a positron, put them together. If we make a B meson, we always make an anti-B meson because we make them with just enough energy that there's nothing else that can happen. So, for example, we could make a negative B meson and a positive B meson. So these are called B mesons because they're the lowest state of what's called of a B quark system. Okay, so then these things decay. They break apart to lighter particles. They do this in all sorts of different ways. One way they can do it is to break apart into this particular final state, where a B plus decays to longer-lived particles called K mesons and pi mesons. So you can make a B plus, which decays to a K plus, K minus, pi plus. And if you add up the charges, you see, oh yeah, that adds up to a positive charge. Or a B minus decays to a K minus, K plus, pi plus. If you look at that, oh yeah, that balances to a B minus. All right, then if you compare the two, B plus goes to K plus, K minus, pi plus, and B minus goes to K minus, K plus, pi minus, you can see that these are particle-antiparticle pairs. So we start with one set of particles, we convert it into antiparticles, and they're exactly equivalent. So if there's no asymmetry in nature between particles and antiparticles, if they behave exactly the same, then you would expect the rates for these two processes to be the same. So if there's no asymmetry between matter and antimatter, we should observe the same number of B plus decays as B minus decays to this final state. Okay, so just this year, well, we haven't quite published it yet. It's been submitted for publication. We measured the process for B plus goes to K plus, K minus, pi plus, versus B minus goes to K minus, K plus, pi minus. So you can look this up on the archive and have a read of it if you like. All right, so here's the yield for B plus. This nice strong peak here. Here's the yield for B minus. This tiny little bit here. So we have this massive asymmetry between matter and antimatter observed in this process. So this is actually the largest matter versus antimatter asymmetry found in nature. There hasn't been a larger one found. So apart from the universal baryon-antibaryon asymmetry, because we haven't actually found any universal antimatter at all. So this is really cool. And it's a clear demonstration that there is a difference in nature between matter and antimatter. So this is kind of cool. There's lots of things you can do about it. One thing you can do about it and use it is define the sign of charge. So the assignment of negative charge to an electron is actually arbitrary. There's no particular good reason why we say an electron is negative and a proton is positive. All the electromagnetic equations would work fine if we swapped these two charges around. If we said an electron is positively charged and a proton was negatively charged. However, with these matter-antimatter asymmetries, we can actually write a definition of charge which is very specific. We can say the charge of the electron is that of the least prevalent B in B plus goes to K plus, K minus, pi plus. Okay? So if we wanted to communicate with a civilization far removed from us who didn't have a good, where we couldn't easily define what was negative and what was positive, this would be a way to do it. All right, so onto the baryon asymmetry mystery. The standard model of particle physics generally does a pretty good job in explaining most of the matter-antimatter asymmetries so far observed in particle physics, maybe with the exception of what we've just found. However, plugging it into the standard model, the early universe predicts a matter-antimatter imbalance of 100 billion to 1, as opposed to what we actually observed, which is a mere 10 billion to 1. So the standard model is way too small by this factor of 10 billion to explain our observed matter-antimatter asymmetry in the universe. And if it was correct, we wouldn't even be here. There wouldn't be enough matter in the universe to make stars and galaxies and all of the things that enable us to exist. So this is a big hint that we don't yet understand matter-antimatter asymmetries, and hence our standard model of particle physics is not complete. There has to be some new physics that we haven't discovered yet, some fundamental new physics that explains why this actually happens. How do we get this big asymmetry in nature? And that's why I'm so interested in this problem and this question. I want to find this new physics, and I want to do experiments where we can look for this new physics. And I think that this is a really good place to look because there's this strong evidence that nature, we don't understand nature. And we should look where we don't understand nature. All right, so there must be stronger sources of matter-antimatter asymmetry. Now, it's actually quite hard to explain our result that we've already observed, but explaining it with conventional standard model might be possible. It could be due to new physics, or it could be due to some very sophisticated interaction of different systems. But there are other hints for a new force in nature to explain the universal baryon asymmetry. So here's one. if you look at the rate for a B meson decaying to a D meson and a tau, compared to the rate for a B meson decaying to a D meson and any other lepton, this is what you measure, this big blob in here. So this is the result of 3 different experiments. So my own experiment in Bell, a competitor called Babar, which ran close to David's apartment in California, and a new experiment at the LHC called LHCb. This is what the standard model predicts down here. This is what's expected from the standard model. So if you look at this measurement compared to what's expected, the difference is what's called 4.1 sigma. So 4.1 standard deviations from what we expect from the standard model. So if probability was correct and we actually understood everything about our experiments and we actually properly understood everything about everything, the chance that this would come out is 0.006. 406. But that's not good enough to claim new physics. To claim new physics, you have to get an order of magnitude smaller than this, 5 sigma. So we need more data. Bell 2 will collect 50 times more data than Bell, the one that which found that really nice asymmetry that I just talked about. So this is a new experiment that we're building now in Tsukuba, Japan, and we're going to upgrade our accelerator to make it 50 times as intense as KEK-B, and KEK-B was the world's most intense collider when it was running. So this is going to be 50 times better than that. And the way we do that is we're going to shrink our beams down from, a massive 2 microns in vertical size to 20 nanometers in size. And by concentrating so many particles in such a small spot, we'll be able to increase the rate of collisions and collect a lot more data in a reasonable amount of time. So Bell 2 is a collaboration between about 700 physicists from 103 different institutions, including Melbourne, Sydney, and Adelaide. All right, so here's the Bell 2 detector. It's a very sophisticated detector. It exists in a magnetic field. There's a lot of instrumentation around it to identify all of the different types of particles that can come out from this. I don't have enough time to talk about the Bell 2 detector because I want to talk about AMS. But what I thought I'd do is show you some events that we expect to see in our Bell 2 detector. So this is actually a simulation of exactly the process that I showed you before, B to K plus, K minus, pi plus. So every click here takes us to a different event. And you can see that they all look very different, even though they're actually making the same final state in one of the Bs. Of course, the other B can do whatever it likes, and there's lots of different ways a B can decay. So all of these different lines here represent the trajectories of charged particles as they come out. If I click on something, what we can do is examine the properties of that particular process. We can look in 3 dimensions at this event as it comes out and examine techniques for identifying different particles and different processes. Okay, so this is what we intend to do with Bell 2. Here's a date on the horizontal axis. Here's the integrated luminosity. So this is a measure of how many collisions we actually make in our detector. As we make more and more collisions, we improve the precision of our measurements, and we go from that measurement that I showed you for K plus, K minus, pi plus. That is actually a 4.9 sigma measurement. So it's not quite 5 sigma. We couldn't quite say we've observed it. So we can say we have a very strong hint. What we want is to say 5 sigma. So we expect to get 5 sigma for this B to D tau, this hint of new physics, in 2020. Okay? Then there are other, I only showed you one, there are 3 or 4 other strong hints of new physics, and then we can collectively knock them off as we go along. And of course, we'll keep looking for strange, exotic things as we keep going along. So for example, we can look for dark photons as we ramp up our luminosity because we will have the world's most intense electron-positron collider, and we'll make very, very good use of it. Okay, so this thing is being built now. Here's one of my colleagues, my good friend Jeff Taylor. And here is our engineer, Tommaso Boncelli, making sure that we record the construction of the inner detector of the Bell 2 experiment. So this is part of our contributions to the Bell 2 experiment, is actually building this inner detector. Okay, so Bell 2 is going well. Yeah, on the May 29th, we actually finished a large fraction of the detector, rolled it in, inserted the beam pipe within it, turned it on, and started looking at cosmic rays, which come from outer space. And we can see that here's event displays of cosmic rays, so you can see that our detector actually works and can observe cosmic ray tracks. And there's actually quite a few Australians involved, 35 in total right now. Okay, so on to AMS. So unlike Bell 2 and Bell, I'm not a member of the AMS collaboration. And what follows is obtained from publicly available material. All results from AMS that I show are from publicly available material. Interpretations are purely my own, and in no way do I speak for AMS. So that's my declaration. Okay, I don't speak for AMS. All right, so this is essentially a particle physics detector placed into space. So here is the International Space Station, and this little thing here is the AMS Detector sticking onto it. So the first thing you might ask, because this thing cost $1.5 billion, is why is it worthwhile looking for antimatter in space? Okay, so the first reason, which is a really good one, is that we can't observe antimatter in the universe that exists in space on the ground because it gets absorbed by the atmosphere. Okay, another good reason for looking in space is there could be antimatter left over from the Big Bang. So remember, we had this massive amount of energy, we make matter and antimatter. Maybe some of that antimatter got left over, and maybe we could detect it if we had a sufficiently sophisticated detector in space. So another good reason for looking is that antimatter, in particular antiprotons and positrons, are predicted to be the final state of what happens if a dark matter particle strikes another dark matter particle and annihilates. So dark matter is essentially its own antimatter particle. This is this idea. All right, so I haven't talked about dark matter at all, but maybe you've heard about it. How many of you have heard of dark matter? Ah, yes. Okay, so it could be that antimatter is a signal for these dark matter annihilations. Another reason you might want to look is there may be exotic cosmological effects that create it. So there are various exotic predictions for how the universe formed, including massive superstring and multidimensional theories, where there might be something called a cosmological defect running through space, and this might be a source of particles and antiparticles. It can tell us about astrophysics in our galaxy, because it's almost certain that antimatter particles will be created when high-energy cosmic rays collide with the interstellar medium, and hence create antiparticles and positrons. And then finally, looking in detail might give us a total surprise. So the AMS experiment is actually a very high precision experiment with lots of different redundant features. So they might be able to detect something unusual. So something that's not a helium nucleus, a hydrogen, a beryllium-7, any sort of reasonable nucleus where you know what the charge to mass ratio should be, because of the precision of this instrument, it might be possible, well, it will be possible, to measure unusual charge to mass ratios. And if we find particles like that, then that's a signature for exotic matter. So it might be that this exotic matter exists in the universe and then we never see it on Earth because it gets absorbed by the atmosphere. So that's another good reason for looking. All right. So if we have high energy cosmic rays, this can collide in the interstellar media to produce positrons and antiprotons. And then these positrons and antiprotons will just sort of float around the galaxy and end up getting detected by the AMS detector. If there are if there are dark matter annihilations, when we have a dark matter hitting another dark matter particle, we might get positrons and antiprotons and so forth, and then these might float around the Milky Way galaxies and also end up at the AMS detector. And then if there's an excess of these antimatter particles from dark matter annihilations, these could be detected at the AMS experiment, and hence be a signal for the existence of dark matter and tell us something about what this mysterious dark matter actually is. So there are a number of ways in which we can look for dark matter. We can collide protons and protons and make the dark matter directly in a collider. We can go deep underground where the backgrounds from everything else that exists, like our radioactive sources, is small, and then look for the tiny weak little signal of a dark matter particle scattering off a nucleus. Or we can look for antimatter in space and look to see if we have an excess of positrons or antiprotons floating around in space. So the alpha magnetic spectrometer, AMS, is designed to do this. It's an international collaboration between all of these different countries and institutions, as listed here, led by Sam Ting. As I said, it's a sophisticated detector with a number of redundant measurement instruments. So at the top, there's something called a transition radiation detector. Underneath that is what's called a time-of-flight detector. Underneath that is a very high-precision particle detector. So what this does is it detects the presence of a charged particle with very high accuracy, and this is embedded in a magnetic field. So this is called a tracker. It's a silicon tracker. There's a magnet which is used to deflect charged particles, so we can determine if a charged particle is a positively or negatively charged, because they'll deflect in different ways in this magnetic field. Underneath this is another time-of-flight detector, then something called a ring imaging Cherenkov detector, and then finally something called an electromagnetic calorimeter. All right, so these are the different components. So the idea is that a matter particle going through this detector will be deflected in one direction, an antimatter particle going through the detector will be deflected in the other direction. And then all of these different instruments give us signals, different signals depending on the type of particle. So for example, we have protons, electrons, positrons, antiprotons, nuclei, antimatter. And then these different particle detectors give us different signals for these different types of particles. So some things like cosmic ray physics and strangelets are these exotic types of matter. So these types of events will tell us if there's strangelets or exotic matter in outer space. These kinds here will tell us whether or not we have antimatter in space, or potentially dark matter, and there's a possibility that we might even detect complex antimatter like antihelium. All right, so the first thing up the top is the transition radiation detector. So what happens is that electrons and positrons emit gamma X-rays when they pass through polyethylene. This is called transition radiation. Then this is detected in X-ray detectors. Protons and heavier particles don't emit this transition radiation. So this gives us a factor of 10 to the 3 differentiation between a positron and a proton. Okay? Positron's positively charged, proton's positively charged. We need something else to tell us whether or not we've got a positron and a proton. This gives us a factor of 10 to the 3 in distinguishing the two. Okay, we have all of these different types of trackers. And all of these trackers have an output that's proportional to how much charge actually goes through them. So this is really useful. This tells us if we have a singly charged particle, a doubly charged particle, a triply charged particle, and so forth. So all of these different elements all have their own different signal. When you add them all together, you actually get a lot of separation between, say, a positively charged, singly charged particle and a doubly charged particle. And that's particularly important for looking for something like antihelium, where the flux is extremely low and you have a massive, massive background of electrons in the case of antihelium. Or, if we are looking for exotic matter, what we're looking for is something that might be fractionally charged. So if something lands between these two, you want to be able to distinguish it with very high precision, and because we have all of these, well, AMS has all of these different means of measuring the same thing, you can add them all together and get very high precision on this charge to mass ratio. Okay, so there's the AMS Tracker. So we measure the momentum of a particle by its deflection in the magnetic field. So the way this works is we have essentially silicon strip detectors. So these are just sort of like solar cells, but with very, very fine features on them, so we know exactly where a charged particle goes through them. My colleague David Jamison is a world expert in this sort of technology. So we distinguish particles from antiparticles by the sign of the deflection. All right. So if we have an antimatter particle going through like this, an antimatter particle going through like this with this sort of deflection, we have a matter particle going through like this with this sort of deflection, in principle we can distinguish the two. However, there's a fundamental flaw if this is all we have. So I just invite you to think about what that fundamental flaw might be. So why do you think this might not work if this is all we have, just the deflection? Anybody? Perfect, brilliant. So, if we have an upwards going particle, that looks exactly like an antimatter particle. So, to solve this, we have, or they have, the time of flight detector. Okay, so we measure the time of flight between the top and the bottom, and so we know if a particle is going in this direction as opposed to going in this direction. So this tells us this is a very important feature of the experiment to know whether the particle is going upwards or downwards. Plus, it's also a measure of the velocity of the particle as well. Okay, then underneath this, we have another redundant measurement of a particle's velocity. This is the ring imaging Cherenkov detector. The angle of the light that's emitted when a charged particle goes through this is proportional to its velocity. So this is another way of distinguishing an electron from a proton, or a positron from a proton. And then finally, there's something at the bottom called an electromagnetic calorimeter. What this does is it absorbs the total energy of an electron, but a proton will actually not leave much of a signal at all, because there's an effect called Bremsstrahlung and pair production, which, because electrons and positrons are so light, they emit a lot of gamma rays and undergo Bremsstrahlung radiation, and then pair production as they go near heavy material. So you can actually absorb gamma rays and electrons and positrons in a very small layer. So this is another way of distinguishing positrons from protons. Okay, on to data. So this is from a paper published last year in Physical Review Letters, 2006. So here is some data of the transition radiation detector sensitivity, it's something like a probability density function, what the signal from the transition radiation detector looks like. If we have particles that are bent in the negative direction, And these are identified antiprotons and electrons. So you can see we can build up this thing called a charge confusion parameter. So this is a very high momentum particle. It's very stiff. It hardly deflects at all in this magnetic field. So there's a chance that because of small deflections or small measurement areas, it will actually come out deflected or appear to be deflected in the opposite direction. But actually, it's not an antiproton, it's a proton. So this is why you want so much redundant measurements, because what you're looking for is something that's so rare underneath a very big background. So this lambda CC is the charge confusion estimator. So there's a nice big signal for electrons, a nice big signal for protons. These are distinguished by the transition radiation detector here. So if you put it all together and look, this is another example from this physical review letter. Look in the momentum range between 5 and 6 GeV. This is the massive signal from protons. This is the nice big signal for antiprotons. This is a nice big signal for positrons. This is a signal for electrons. And then these are pions, which come about through interactions in the actually AMS detector. All right, so these are the results that AMS actually measured and published in this paper. All right, so the red circles are antiprotons, and what we have here are a lot of units that actually measure the flux. So how many charged particles going through the AMS detector in a particular region. So it's all nicely normalized so that you can actually calculate explicitly and directly, numerically, how many electrons, positrons, protons, and antiprotons actually went through the AMS detector. All right, so here's the antiproton flux. Here's the positron flux, these green dots. Here's the proton flux, these open circles here. And here's the electron flux. Now, they put all of these on the one plot, but they actually all have different units because it's just too hard to see it all on the different scales. So perhaps a different way of looking at it is to normalize it relative to the proton flux ratio. So here's the number of antiprotons divided by the number of protons, measured by AMS. And you can see that it's almost flat. And the unit here is 10 to the minus 4. So this is 2 by 10 to the minus 4. So 2 in every 10,000 charged particles in outer space are actually antiprotons. So that's actually quite a few. There's a lot of charged particles in outer space at high momentum, and quite a large fraction of them are antiprotons. Moreover, they go out to very high momentum, okay, well over 300 GeV. Here's the ratio of antiprotons to positrons. Okay, and you look at this number and you can see it's 10 to the minus 1 here, so this is like 0.5. Okay, so the flux of antiprotons compared to positrons is really quite high. There's a lot of antiprotons in outer space, and there's a lot of positrons. So consequently, the flux of protons to positrons is also constant to very high momentum as well. So all of this is was kind of surprising when it first came out. And people were surprised. We didn't expect to see so many antiprotons and so many positrons at such high momentum. And there are a whole class of different dark models invented to account for this. However, as astrophysicists got more and more sophisticated, they began to look at how cosmic accelerators that actually make these high-energy cosmic rays actually work, and what the densities of pulsars actually could be, and they compared this to data. All right, now AMS is a cool experiment, but it's by no means the only game in town. There's a lot of other experiments out there. So this is, for example, the Pamela experiment, the Pamela satellite. And actually, it's the data from Pamela preceded AMS and caused a lot of the initial fuss, as did data from the Fermi satellite experiment. HESS is a Cherenkov telescope array. They're actually located on the ground, and they're a collection of mirrors where light from cosmic rays making Cherenkov light in the upper atmosphere is focused onto photomultiplier detectors. So it's a means of detecting very high energy cosmic rays. And you can see that the data from HESS goes way beyond where AMS can go. And then there's another very interesting experiment which just uses old-fashioned technology, a balloon, which was put into orbit around Antarctica. So Antarctica has westerly flowing winds that circulate around and around it. If you put a balloon up in Antarctica, it'll happily go round and around Antarctica and collect a lot of data very high up in the atmosphere. All right, so if you take this model and you fit it to the AMS data, you can predict all sorts of interesting things. Using the latest cosmic accelerator models, which include all of the potential supernova and supernova remnants, all of the pulsars that might be present in the Milky Way galaxies, the data can actually be reproduced given the range of parameters of the models. So this is actually the proton to positrons to anti-proton flux predicted, and you can see that this model actually does pretty well with that, all the way out to high momentum. Okay, so one last little tidbit. So Sam Ting is a very famous physicist who is very strong proponent of his experiment. But he's also very careful. So AMS, in this presentation made at CERN last year, reported a few anti-helium candidates. That's what they said. We found a few anti-helium candidates. Now, finding these requires suppressing all of these backgrounds that I talked to you about to 1 in a billion of their original rate. Okay? So all of this redundancy that's in the AMS experiment is absolutely vital in order to be able to distinguish these. And physicists worry that perhaps something went wrong because this is very, very highly suppressed. And it could be some background that's fluctuated up that looks like these helium nuclei, these anti-helium nuclei. Now, these events were not shown in the presentation. Sam just reported them just like this. They weren't shown in the presentation. So the first question is, are they real? The second question is, if they are real, what does it mean to have these few anti-helium candidates? So actually, you know, my gut feeling is that this is, these are created in these very, very high energy cosmic ray collisions and aren't a particular source of primordial antimatter. However, we don't know anything about them. Maybe they're all low momentum, in which case that would be really interesting. If they're very high momentum, they're almost certainly made in cosmic ray processes. Okay, so in summary, the universal matter-antimatter asymmetry remains. We would love to know what the cause of it is. We're really keen to find out, and we have a next generation of experiments that may tell us what the origin of this is. So this is one of the fundamental issues requiring new physics. So this is one of the reasons we know the standard model of particle physics is not complete. So in the next round of experiments, Bell 2 and our friendly competitors, LHCb at CERN, will address this and other hints of new physics. And this will be really, really fun. We're just about to turn on next year. LHCb is about to go through another round of upgrades. We'll be very competitive as we go forward. They'll be good at some things, we'll be good at others. There'll be places where we're both equally good and we can check on one another. Precision measurements of antimatter and cosmic rays have not yet found new physics. However, the data do provide valuable contributions to astrophysics and constrain models of new physics. So, for example, if there was a certain abundance, if the abundance of dark matter was sufficiently high and they annihilated in just the right way, then you would expect a larger flux of antiprotons than we actually observe, and those models have now been ruled out. So that's where I want to finish. Thank you very much.
Well, Martin, thank you very much for that lecture. I must say, ladies and gentlemen, when you're heading home on the tram tonight, you'll be able to tell the person you're sitting next to you just saw a bit of antimatter splashing around in a lecture theatre at the University of Melbourne, which reminds me I better be careful with the Dean of the MSD. I promised not to mess up his theatre with the physics lecture tonight. So, ladies and gentlemen, we've got time for a few quick questions before we bring the proceedings to a close. Okay, sir, one very quick question from down the front here.
Thank you for a beautiful lecture. I remind you what relationship between antimatter and dark matter. What the relationship between antimatter and dark matter?
Almost nothing. So we really don't know what dark matter is. We understand very, very well what antimatter is. So as you've seen, we can make that in this lecture theatre. It's not hard to make antimatter at all. We don't know anything about dark matter. Well, we do know we know a reasonable amount about it, but its origin remains very, very mysterious.
Yes, sir.
No, we know it's not inflation. I simplified the discussion. There's actually a lot of other things. There's actually 3 criteria we need in order to make the matter-antimatter asymmetry, one of which is that the process has to be out of thermal equilibrium. So the inflationary period is nicely out of thermal equilibrium, but it happens so early in the universe that if there is any asymmetry present there, it'll get washed out in other phase changes later on as the universe expands. Actually, I'm not a theorist. Let me think that through. There are various people who can invent theories where inflation does cause it.
Yes, sir, in the middle of the theatre there. Please speak very loudly.
Okay, so the most compelling reason is that we know how much mass there is in the universe. We can measure the amount of light, and we can relate that to how much mass there is in stars and galaxies, and through gravitational lensing and so forth. So we can work out how much matter there actually is in the universe. The other thing that we can measure is the cosmic microwave background. So the cosmic microwave background tells us how many photons are present. So if you count how many photons are present and how many baryons are present, it's 1 part in 10 to the 9. There's 10 to the 9 times baryons, 10 to the 9 times more photons than baryons. If you plug the matter-antimatter asymmetry from the standard model of particle physics into the early universe, that ratio is decreased from 1 in 10 to the 9 to 1 in 10 to the 20. So there's just too many photons for there to be equal amounts of matter and antimatter.
Martin, I might we'll just take one last question before we wrap up. Please again speak loudly.
Okay, so with the release on asymmetry which you measured just earlier this year, is that consistent with the baryon asymmetry which you quoted as 10 billion to 1, I think you said?
No, we really don't know how to map that into the standard model at all right now. There's actually no model that will reproduce the results that we showed today.
So if I may ask the final question, Martin, in the G-bar experiment, after my colleagues have trapped the antiprotons, combined them with an anti-electron to make an anti-hydrogen atom, and then release it from the laser trap where it was made, do you think it will fall up or will it fall down?
I would bet you $1 it'll fall down.
Oh, okay. So I think it's going to fall.
But
All
that's
right.
only because I'm a total cheapskate. I would fall off my chair if it fell up.
Well, let's hope for a surprise. That's what physics does over the years. Always there are surprises, testing human ingenuity, and we've seen a lot of human ingenuity at work here tonight. So, ladies and gentlemen, let me just get ready to wrap up our 2017 July lecture program. I should mention that next year it will be 2018. This will be the 50th anniversary of our long-running July Lectures in Physics program. Programs of lectures addressing fundamental issues in physics. So I'm thinking next year we should do something to reflect that over the past 50 years, much of the physics that we've heard about tonight and in the previous lectures would have been an enormous surprise to our colleagues from 50 years ago. So I'm going to try and recruit some colleagues who can talk about what physics might be like 50 years from now, which we'll present to you in 2018. So before I close, let me thank a few people. I'd like to thank Steve Damon, who I hope hasn't been annihilated. No, he's still with us. Good on you, Steve. Thank you very much. Steve has done a sterling job setting up all the demos, and we couldn't bring you such demos of such sophistication without Steve's help. I'd like to thank Graham O'Keefe, who was brought in from the Austin Hospital, the antimatter used in medical diagnostic imaging so that we could demonstrate real live antimatter events here in the theatre tonight. Graham, thanks a lot. I'd like to thank the Penny Fairbank and Carl Brown and the other people who have been running the back office and managing the bookings and all the rest of it. I'd like to thank all the speakers. And ladies and gentlemen, I'd like to thank you, the audience, who turn out to come to our lectures on a very cold Friday night in Melbourne. It's the feedback we get from you and the audiences that make this program so rewarding for us to present year after year. And I look forward to welcoming you all back for the Physics in the Future campaign in 2018. Thank you very much, and safe travels back home.